Assalamualaikum and hello everyone. Um, this is my second video about chapter 4 digital modulation and transmission. So in my previous video I have explained about the basic concept of digital modulations. I have explained about the basic principle of changing the analog signal into digital signal. So we have learned about sampling process, quantization process, and also the encoding process, where we have seen the signal have changed from analog into PCM code word. Okay, and I also have explained about this topic, which is the signaling rate, bit rate, and also the bandwidth of the PCM. Okay, so I want to continue again about this chapter so that we can complete this chapter 4 in this week, and hopefully in next week we can begin begin our class in chapter 5 regarding the uh, the topic of uh, antenna and also the wave propagations. Okay, so uh, so back to this topic. In my previous video, I also have start explaining about this. So I want to refresh again about this topic. So in PCM, okay, we have three main parameters, which are the signaling rate, or we call it as a sampling rate, the bit rate, and also the bandwidth of the PCM. Okay? So sampling rate, SR, is equal to 2 times highest signal frequency FM. So this is the minimum sampling rate according to Nyquist theorem. Okay, remember that Nyquist theorem said that the minimum sampling rate must be equal to the 2 times the highest frequency of message signal. Okay, so this is the minimum. So this sampling rate define how many sample should we take within 1 second. Okay, dia menggambarkan dia satu parameter yang menggambarkan berapa banyak sampel yang perlu diambil dalam masa 1 saat. Okay, so sampling rate SR is equal to 2 FM, and the unit is in term of sample per second, or we can say in term of hertz. Okay, and then we have the second parameter, what we call as the bit rate, or you can see also this is the data rate actually. So bit rate is equal to sampling rate SR multiplied with the number of bit per sample. Okay, so we have a sample per second. Okay, so sample per second multiplied with number of bit per sample. Okay, so uh, the output, okay, the output of this equation, this formula, we're gonna produce a bit rate with a unit of bit per second. Okay, number of bit per second. So this bit rate, or we can also call it as a data rate, define the speed of transmission. Okay, how many bits that can be transmitted from transmitter to the receiver. Okay, so the speed of transmission is defined by the bit rate parameter, or we call it as a data rate. Okay, and then we have another parameter, what we call as the bandwidth. Okay, so the bandwidth of PCM is depending on the bit rate and the waveform pulse shape, either sync function or rectangular, used to present the data. So in the sampling process, we should take note whether we use a sync function for the sampling or we use a rectangular pulse train for the sampling. Okay, so both of these are going to produce a different different bandwidth values. Okay, so if you use a sync function, that means we're going to produce the minimum PCM bandwidth. Okay, so the minimum PCM bandwidth is equal or more half of the bit rate. and the unit is in term of hertz. Okay, so the minimum of PCM bandwidth, this is obtained if only when we use the sync function during the sampling process to generate the PCM waveform. And we have another values for the bandwidth if we use a rectangular pulse train during the sampling process. So if you use a rectangular pulse train during the sampling process, we're gonna produce a bandwidth equal to the bit rate. Okay, so this is normally what we said. So this is normally when we said about bandwidth of PCM. So bandwidth of PCM is equal to the bit rate. Okay, so the unit is in term of hertz. Okay, so the bandwidth of PCM, for example, 1 megabit per second for the bit rate. So this is equivalent to 1 megahertz for the bandwidth. Okay, so normally when we said about bandwidth of PCM, so we say that bandwidth of PCM is equal to the bit rate. Okay, so I'm gonna pause for a while. Okay, so bandwidth of PCM. Okay, bandwidth of PCM. Normally, when we say bandwidth of PCM, we say that bandwidth of PCM equal to the bit rate, because most of the time in practical cases when we produce the PCM waveform, we are actually using the rectangular pulse shape during the sampling process. So, in most cases, bandwidth of PCM is equal to the bit rate. So as I said previously, if the bit rate is in 1 megabit per second, that means the bandwidth is 1 megahertz. Okay, so remember that bandwidth, the unit for bandwidth is always in terms of hertz. And example for these parameters, okay, an analog signal with frequency 40 kilohertz, okay, is sampled at sampling frequency equal to the minimum Nyquist sampling frequency. Okay, so we have the signal frequency, which is this is input message frequency. So this is sample to the minimum Nyquist rate. Remember, Nyquist said that the minimum sampling rate Fs is equal to 2 Fm. Okay, so this is according to the Nyquist theorem. And each sample is encoded using 4 bit of PCM. Okay, so we use a 4 bit. That means the value of n is equal to 4. Determine the bit rate, which is BR. So in order to determine BR, first we need to find the sampling rate. Sampling rate, according to Nyquist, so since we are sampling the minimum rate, so Fs is equal to 2 Fm. So therefore, this is equal to 2 times 40 kilohertz, and therefore the sampling frequency is equal to 80 kilohertz. Okay, so from this sampling rate, we can find the bit rate, which is sampling rate multiplied with the number of bit per sample. So 80 kilohertz multiplied with 4 bit. So we're going to produce bit rate equal to 320 kilobit per second. Okay. And for the example 6.8, okay, the bit rate of pulse code modulation transmission is fixed at 63 kilobit per second. So this is the bit rate. Calculate the bandwidth. So this question does not specifically mention what kind of waveform that we use for the sampling process, either sync function or the pulse train. It simply mentioned about the bandwidth of PCM. So in this case, what you can do is that you can say that the bit rate the bandwidth of PCM is equal to the bit rate of the PCM, which is equal to the 63.63 kilohertz. Okay, so if the question specifically mention about a minimum PCM bandwidth, so therefore you can say that the minimum bandwidth of PCM is equal to half of the bit rate. Okay, so in this is a very general questions. So just remember that what you can do is, if this is the question asks you about the bandwidth of PCM, simply say that we can give a simple answer: bandwidth of PCM equal to the bit rate. Okay, which is 63 kilohertz. Example 6.9. So this example is similar to the questions that have been asked in the previous final exams. Okay, previous semester final exam. So this question is among the favorite question has been asked in the previous final exam. So if you see from here, this is about some bit rate and also the bandwidth of PCM. So what about if we sample more than the Nyquist theorem? Okay, so if you read the question, an analog signal with frequency 4 kilohertz. So you are given the input message frequency FM is sampled at sampling frequency 10 times higher than the minimum Nyquist sampling frequency. So that means you are sampled 10 times higher than the minimum sampling rate, which is 2 FM. So each sample is encoded with 3-bit PCM code. So this is you are using 3-bit before it's transmitted into the channel. Determine the bit rate BR. Okay. So in order to determine the bit rate, first of all, you need to find the sampling rate. Okay. So sampling rate, according to Nyquist theorem, the minimum sampling rate is 2 FM. Okay, first we determine what is the minimum sampling rate according to Nyquist. So Nyquist said that the minimum sampling rate Fs is equal to 2 FM, which is 8 kilohertz. But the question said that we are actually sampling 10 times higher. So how much is the new Fs? How much is the sampling frequency that we use in this process? Okay, so the actual sampling frequency is 10 times higher than the Nyquist theorem. So therefore, it is equal to Fs, the minimum sampling rate, plus 0.1 Fs. Okay, because we are sampling 10 times higher. 10 times higher than the minimum sampling rate. Okay, so this is the minimum Fs, the minimum sampling rate, plus 0.1 of Fs. Okay, so plus 10% higher. Okay, dia adalah 10% lebih daripada minimum sampling rate. So this is equal to 8 kilo 8 kilohertz 8 kilohertz plus 0.1 multiplied with 8, so you get 0.8 kilohertz. Okay, so this is actually 0.1 multiplied with 8k, so you get 0.8 kilohertz. So therefore, the sampling rate is equal to 8.8 kilohertz. Okay, so or you can see that this is actually 8.8 kilo sample. Okay, 8.8 kilo sample per second. You can also say in terms of kilo sample per second, no problem. Okay, so from here, from Fs, we can determine the bit rate BR. So bit rate BR is equal to 2 times, okay, sorry, BR is equal to N multiplied with SR. Okay, so N is number of bit that we use is 3-bit multiplied with our sampling rate 8.8 kilohertz. So 8.8k multiplied with 3, we get 26.4 kilobit per second. Okay, so the bit rate or the data rate is actually equal to number of bit multiplied with the sampling rate. Here sampling rate is 8.8, so therefore we produce bit rate equal to 26.4 kilobit per second. And then the bandwidth. The question asks bandwidth of PCM. So bandwidth of PCM, as I mentioned earlier, bandwidth of PCM actually equal to the bit rate, which is equal to the 26.4 kilohertz. Okay, same as this one, but the unit is in term of hertz. Okay, so we produce 26.4 kilohertz. So we actually need the bandwidth. Okay, in order to support this bit rate or data rate, we need bandwidth about 26.4 kilohertz. Okay, uh, untuk mendapatkan bit rate seperti ini, untuk melaksanakan bit rate untuk menghasilkan bit rate seperti ini, kita memerlukan bandwidth sebesar 26.4 kilohertz. Okay, so because if we want to transmit at higher rate, okay, remember that if we want to transmit at higher rate, we need more bandwidth. Remember that bandwidth and bit rate are correlated to each other. It is directly proportional to the it is directly proportional to each other. Okay, bandwidth is proportional to the bit rate. Okay, the higher the bit rate, the higher would be the bandwidth that we need. Okay, so baseband transmission. Okay, so baseband transmission is a transmission that we use using a low frequency. Okay, using the original frequency of the input. So we are not actually modulate with the RF carrier. We are still using the original frequency from the input. Okay, kita tidak melaksanakan modulation dengan RF carrier yang mempunyai frekuensi yang tinggi. So in this case, in the baseband transmission, so baseband transmission normally, most of the time, it is used for the wired transmission normally. Okay, where we do the before we transmit the PCM code word, we are actually doing the encoding process using the line coding method. Okay, sebelum kita hantar PCM code word itu yang kita produce, that we produce after the encoding process. So before we transmit, we need to change the code word into the electrical pulses which is suitable for transmission. So kita perlu tukar PCM code word itu kepada electrical pulses yang bersesuaian untuk transmission. Okay, so in this case, since we are using a low frequency, the original frequency, the base frequency of the input, that means we are actually do the baseband transmission. Okay, so in this case, there is no carrier, there is no analog carrier involved in the process. Okay, dia tidak melibatkan proses modulation dengan analog carrier. What we do is actually we do some sort of encoding process where we change the code word into the electrical pulses in terms of voltage, digital voltage that is suitable for the transmission. So in order to do this, we can use a line coding, what we call in general, what we call as a line coding. So line coding, we have a lot of line coding method. For example, we have a non-return to zero, NRZ, phase encoded, return to zero, and also multi-level binary. Okay, so here the PCM code word, actually we change it into electrical pulses, but here we have the options either to use a unipolar or bipolar. Okay, so unipolar means that we have only single polarity. Okay, single polarity positive voltage, or we can also produce bipolar where we have the two polarities. Okay, positive voltage and also the negative voltage. Okay, in terms of different polarities. Okay, so this is what we call as a unipolar, because we have only single polarity positive voltage, we produce a positive voltage. Or here we have a bipolar, Bipolar means we have two polarity output, positive and negative voltages. Okay, so this is the example. So this is the first picture here. So you see that, sorry, the above picture A is the PCM code word, PCM sequence that we produce after the encoding process. Remember, this is a PCM code word, PCM code word that we produce after the encoding process. So now when we do the when we do the process of baseband transmission, actually we do the encoding process using the line coding method. Okay, so the output of the line coding, either we can produce a unipolar PCM output. So this is, you see that we have this is only positive voltage, and here also the picture below we have the bipolar. Okay, so we change the code word into a bipolar PCM waveform. So this is we can say that this is a PCM waveform actually, both of these. Okay, the unipolar and bipolar, where we change the code word into a electrical pulses. So in bipolar we have positive, we produce positive voltage and also the negative voltage. Okay, so bipolar, remember that bipolar we have two polarities of the PCM waveform. So these, both of these, unipolar and also the bipolar, this is the PCM waveform that we transmit to the channel. Inilah dia bentuk PCM waveform yang kita hantar daripada transmitter kepada receiver melalui channel. Okay. So this is different from the analog. Remember, in analog waveform, we have infinite shape. Okay, we have infinite shape of analog. So now in digital waveform, we have two types, unipolar or bipolar, where it only have two states, logic 1 and logic 0 only. Okay, and this is the PCM waveform. Okay, this is the PCM waveform. There are that we can produce using line coding. Okay, I can see this is using a line coding. Okay, so line coding has many types. Okay, you have NRZ, RZ, RZ AMI, alternate mark inversions, Manchester coding, and many others. Okay, so I will explain to you the simplest one. Okay, the simplest line coding. So you see that here we have the input here. Over here, the above part here is the input. Okay, so this is the PCM. So this is what we call as the PCM code word. Okay, PCM code word. Okay, so PCM code word here is 101100001101. So how do we want to convert this into electrical pulses? So the issue now here is, how do we convert the PCM code word into electrical pulses? Itu isunya sekarang. So in order to convert it, we can use line coding. So first of all, we can see from here using NRZL, non-written zero dash L. L here means level. Okay, so remember that non-written to zero. Okay, you see that here non-written to zero is a bipolar line coding technique where we have two polarities. Non-written to zero means that the waveform is not returning to 0 volt. Instead, it will be alternate into different polarity. So you see that for the first here, if we have input 1, okay, you see that input 1 and then input 0, it will change to negative. Okay, negative voltage. So what happened here is actually every time we every time the input sequence of 0, the polarity will change from positive to negative. Okay, so you see that uh, okay. Okay, so for NRZL, okay, every time the input is 0, you're going to produce the output of negative voltage. Okay, logic 1 will produce positive voltage, logic 0 will produce negative voltage. Okay, so in here, what you can see here is that every time there's a change of logic state from 1 to 0 or 0 to 1, you're going to see the output is changing in terms of polarity. Okay, so you see that here logic 1 will produce positive voltage, logic 0 it will produce negative voltage, and so on. Okay, and then here is NRZM, non-return to zero mark. So what happened here is that the output will change polarity every time every time we have input logic 1. Setiap kali ada input logic 1, maka polarity akan bertukar. So this is what we call as a non-return to zero mark. So it gonna check the input for logic 1. So every time there's a logic 1, it gonna change the polarity. Okay, so let's see here. The input first is logic 1, so positive voltage, and then logic 0 input, no change, tidak ada perubahan. Then the input is logic 1, so it gonna alternate the polarity, so polarity becomes the output will produce negative voltage. Then the input is logic 1 again, so it will change the polarity into positive output voltage. Then the input is logic 0, so no change in polarity. And then logic 0, no change in polarity, no change in polarity. Then logic 1, change polarity from positive to negative voltage. Okay, and then logic 1 again for the input, so change polarity into positive voltage. Then logic 0, no change, and then logic 1 change polarity. Okay, so this NRZM is depending on the logic input 1, where it will change the output polarity. Okay, and then non-return to 0 S for space. So this one is inverse of the NRZM. So in NRZS, it will alternate the polarity of the output when the input is logic 0. So dia terbalik Tadi logic 1 baru dia tukar polarity. Now logic 0 will change the output polarity. Okay. So you see here that initially so you see that the initial, it doesn't matter. Initial, if you want to start from negative or you can start from positive, it doesn't matter. Okay, for the initial state. Okay, for the initial process. And then you see that the next input is logic 0, so it will change from negative. Initially it's negative, change to positive. And then input logic 1, no change. Input logic 1, no change. Input logic 0, so now it will change the polarity from positive to negative. And then input logic 0 again, change polarity to positive. And then input logic 0 again, so it will change polarity from positive voltage to negative voltage. Okay, and then you see that here is input logic 1. So input logic 1, so no change in the output, no change. And then input logic 1 again, no change in the output polarity. And then the next input is logic 0. So logic 0 will alternate the output polarity from negative voltage to positive voltage. Okay, and then input logic 1, so no change in the output polarity. Okay, and then we can see from here the unipolar RZ, unipolar return to zero. So that means the output will always return to 0 volt. Okay, so the output only change for half of the bit time. Okay, so what is the bit time? So I should explain to you previously that the bit time is the time for the one bit. Okay, time taken to process the one bit. Okay, t here, so this is t for one bit. Okay, the time taken for the to represent one bit. Okay, berapakah masa yang diperlukan untuk represent satu bit? Okay, bit time. So unipolar, you see that for unipolar return to zero, so the output waveform will change only for the half bit time. Separuh masa bit akan bertukar. So in this case, if you see here, unipolar return to zero. Okay, so unipolar return to zero for every time there is an input one, it will produce output of positive polarity. Okay, and it will return to zero again. Okay, setiap kali ada input logic satu, dia akan menghasilkan output positive voltage and then return to zero. Okay, so you see that here the first input is logic 1, so logic 1 will produce output positive. Okay, positive output for half bit time, and then another half bit time it will return to zero. Dia akan sentiasa return to zero. And then the next input is logic 0, so it will remain at 0 volt. Okay, nothing changed, nothing happened. And then input logic 1, it will produce output positive and then return to zero. Input logic 1, again produce output positive, return to zero. So the next input is logic 000, so no change in the output. And then input logic 1, so it will produce positive output and then return to zero. Okay, so positive output return to zero, and then input logic 0, it will maintain at 0 volt. And then the next one is input logic 1, so logic 1 will produce positive output voltage and then return to zero. Okay, and then we can see from here bipolar return to zero. So now we have two polarities of output, positive polarity and negative polarity of voltages at the output. And this is for the type of return to zero. So that means half of the bit time is to change the polarity, and then it will return another half time is to return to zero. Separuh masa adalah perubahan voltage dan separuh masa bit lagi adalah untuk kembali kepada 0 volt. Okay. So in bipolar return to zero, logic 1 will produce a positive output voltage, and then logic 0 will produce negative output voltage. So both of these will return to zero for half of the bit time. And you see that here for the input logic 1, it will produce positive output voltage, return, and then another half of the time return to zero. The next input is logic 0. So logic 0 will produce negative output voltage for half bit time and then return to zero. And then the next input is logic 1. It will produce positive output voltage, return to zero. Another logic 1, so positive, return to zero. And then we have three zeros for the input, so it will produce negative output, return to zero, negative output, return to zero, negative output, return to zero. Then we have input 1, logic 1 and logic 1, so it will produce positive 0, return to 0, positive, return to 0. And then logic 0, it will produce negative output voltage, return to 0. And then logic 1, positive voltage, return to zero. Okay. And then return to 0 AMI, alternate mark inversion. So in this case, this is type of a return to 0. That means it will alternate the output polarity every time uh, every time we have an input of logic 1. So setiap kali ada logic 1, dia akan change polarity for half of the bit time and then return to 0. Okay, so you see that here initially we have input logic 1. So for the initial state, so in this case it assumed as positive. Okay, this is for the initial state. So you see that half of the bit time is for the output positive voltage. In this case, separuh masa bit adalah untuk uh, perubahan dari polarity. Okay, so half of the bit time is used for to change the polarity, and then it will return to 0. Okay, so and then you see that the input is logic 0, so no change, it will remain at 0 volt. Then the input is logic 1, so every time we have a logic 1, it will change polarity. So previously is positive voltage, now it will change to negative voltage, half of the bit time, and then return to 0. Then the next input is logic 1. So it will change the polarity from previous based on the previous output. So previously is negative voltage. Now it will change to positive output voltage. Okay, and then return to 0. So and then the next three input bits are logic 0. So logic 0 will not produce will not change anything at the output, so it will remain at 0 volt. And then the next input is logic 1, so it will alternate the polarity. So previously is positive, so now becomes negative output voltage for half of the bit time, then return to 0. Then another input 1, so it will change the polarity from negative to positive, half of the bit time, and then return to 0. And then logic 0, no change. And then logic 1, change polarity from positive to negative, return to, and then return to 0. So this is how they define the output of the PCM. Okay, the PCM waveform that will be transmitted along the channel. Okay, so this is in terms of waveform. You see that this is actually voltage versus time waveform. This is actually in time domain. Okay, where we only have the input is only logic 1 and logic 0. So this is very different from the analog signal where it is continuous over time. Okay, so here the pattern is the pattern we can see the pattern, okay, in the waveform. It's different from the analog where it has infinite shape. Okay, so it is for the analog is different for us to determine the related pattern. Okay, there's no specific pattern for the analog actually. So it's quite is very challenging to do the signal processing for the analog actually. Okay, so these are the definitions, these are the explanations for all of the PCM waveform. So non-return to 0, return to 0, NRZ, and so on. So here this one you can read on your own about each of the waveform, PCM waveform. Okay, so there are many line coding methods. You can read this and understand on your own. So I will continue to the next topic, which is the digital modulation. Okay, so digital modulation here, if you see from here, digital modulation in this topic means that we want to transmit the signal, okay, the digital data into wireless medium. Okay, so in this case, when we want to transmit digital data through the free space or through the air, okay, so we need to transmit uh, using as a electromagnetic waveform. Kita perlu hantar dalam bentuk electromagnetic waveform. So if you want to transmit signal in term of in the free space as a electromagnetic waveform, what we need is that we need a carrier. Okay, we need a carrier. So therefore, we need to modulate our digital data with the analog RF carrier. Okay, that means the carrier has a higher frequency in radio frequency. Okay, so this carrier has a higher frequency depending on the applications. It can be in megahertz, gigahertz, or other frequency values depending on the system application design. Okay, so carrier ni dia mempunyai frekuensi yang tinggi dalam julat radio frequency ataupun dalam julat gigahertz, terahertz dan sebagainya. So it depending on the system design. Okay, so now we have you see that in digital modulation we have the digital data. Okay, logic 1, logic 0, logic 1, logic 0, logic 1, logic 0, and we want to modulate. Okay, we want to modulate with analog carrier. Okay, we want to modulate with analog carrier so that we can transmit the signal wirelessly in the channel. Okay, through the channel. So here, so this is in digital modulation. The techniques is quite similar with the AM in the with is quite similar with the analog modulation in that we have learned in chapter 3. So when we modulate with the analog carrier, actually it will change the characteristic of the carrier. Okay, remember when we modulate with the carrier, what happened is that the characteristic of the carrier will change according to the input. Okay, remember that our input only have two states, logic 1 and logic 0 only, different from the analog system where the input has infinite states. Okay, dalam analog input mempunyai states yang berbeza, infinite, dia tidak tentu dia ada pelbagai. Where in digital we only have two possibilities, two states only, logic 1 or logic 0. And this digital data will change the characteristic of carrier in terms of amplitude or in terms of frequency or in terms of phase also. Okay, so now if the modulation change the amplitude characteristic of the carrier, we call it as ASK, amplitude shift keying. If the modulation change the frequency characteristic of the carrier, we call it as FSK, frequency shift keying. And if the modulation change the phase characteristic of the carrier, we call it as a PSK, phase shift keying. Okay, and then okay, so this is the basic digital modulation techniques: ASK, FSK, and PSK. So ASK is we can say that it is quite similar. Okay, not same, quite similar with AM in the analog. FSK is quite similar with FM in the analog. PSK is quite similar with the PM in the analog. Remember, this is I say that similar. It is not the same, but it is looks similar process. The process looks a little bit similar, where it changed the characteristic of the carrier. Okay, and this is the basic block diagram for digital modulation. Okay, so previously we have the input data, and then we have the precoder. Okay, so precoder, we encode the signal. Okay, so we encode the signal. That means we're going to do the changes of analog to digital. So we have the digital data. So the output here is we have the digital data 101010, and then we modulate with the analog carrier. Okay, so modulate with the analog carrier. So, and then we can have a band pass filter to filter the only the certain frequency that we want, and then we transmit through the channel. So in the channel we have noise, and then at the receiver, so this signal receive at this. So you see that what we transmit here is actually we are transmitting analog signal actually. Okay, the analog signal carries digital data. So that's a different thing, you see. So different from the analog system in chapter 3 that we have learned so far, where the analog signal carries analog data. That one is different. Okay, so now here is we transmitting analog signal, but the analog signal carries digital data. That's the difference. Okay, so we transmitting analog signal which carries the digital data and then receive at the receiver, and then we filter out and amplify, and then we do the demodulation process. Okay, and then we can have the output. So output here, again, if the output here is the analog, so if the input is analog, that means we're going to produce analog at the output. Okay, energy bit over noise density, which is EB over N0 and not. Okay, so EB is equal to the average bit energy, N0 or N0 is equal to thermal noise power density. So the formula is EB is equal to receive power in watt multiplied with the bit time, bit duration, okay, in second. So this is actually watt multiplied with second or watt second. Okay, and then N0, N0 is equal to KTN, Boltzmann constant multiplied with Tn here is a noise temperature at the receiver. Okay, noise temperature referred to the receiver input. So we are actually measuring this parameter at the receiver side actually. Okay, where we have PR, the receive power, and then we have the N naught which is equivalent to KTN. Okay, so what is EB over N0 here is this is the important parameter which is I can say that similar to the SNR in the analog. Okay, in analog we use the SNR, but in digital most of the time we normally use the EB over N0. Okay, lebih it is more practical to use EB over N0 other than it is better to it is more practical if you use the EB over N0 compared if you use the SNR signal power to noise power. Okay, so this is very important parameters. So in this, in your syllabus, EB over N0 is not really learn uh, very details. Okay, just very surface about this EB over N0. And then we have another parameter, important parameter, what we call as the channel capacity. So channel capacity is actually define the maximum bit rate or the maximum data rate that can be transmitted by the transmitter to the receiver so that the receiver can do the decoding process. Remember that this channel capacity define the maximum bit rate or define the maximum data rate that can be transmitted by the transmitter. Okay, so this if the transmitter follow these capacity values, that means the receiver is capable to decode the transmitted signal back to the original input data. Okay, so if transmitter transmit more than the channel capacity, what happen is that the receiver will be unable to decode the transmitted signal. Okay, there's gonna be a lot of error, and it will produce a very bad output. So itu yang berlaku sekiranya transmitter menghantar pada kadar yang jauh yang lebih besar daripada channel capacity. What happen is that the receiver will be unable to decode. Okay, so this channel capacity is also depending on the bit error rate of the channel conditions, and also the ability of the receiver itself. Okay, so kalau transmitter menghantar lebih daripada channel capacity ini, maka outputnya akan mempunyai kualiti yang sangat teruk. So channel capacity here is defined as 2 times bandwidth multiplied log to log base 2 of m, and the unit is in term of bit per second. Okay, so bandwidth, minimum bandwidth. Okay, minimum bandwidth necessary to pass a M array digital modulated carrier, which is equal to B here is the bit. This is the bit rate. B over here is the bit rate divide with log to base m. Okay, m is you see that what is m actually? M is equal to 2 power of n. Okay, m is equal to, so m is equal to 2 power of n, or number of bits. So here it use k, it doesn't matter, so it is a 2 power of k here, and if you use the n is also the same, this is a number of bit. Okay, so m define the number of symbol actually. Okay, so because in here sorry, in PCM we are actually transmitting one bit, actually one bit at a time. Okay, so in PCM it is actually 2 power of 1. Okay, because we are using one bit only, so we have two symbols, okay, which is a symbol for logic 0 and logic 1. So we have two symbol. If you use a 2 bit, okay, if you use 2 bit, that means 2 multiplied 2 power of 2, so you have 4 symbols, m equal to 4. So what is the 4 symbol? You see that the 4 symbol is actually 0 0 0 1 1 0 1 1. Similar with if you use 3 bit, you have 2 power of 3, that means you're gonna have 8 symbols. So in digital, actually you see that we have ASK, FSK, and PSK. So actually it has this the way we write the type of modulation, in the type of digital modulation, we have ASK, we have FSK, and also PSK. So all of these, each of these digital modulation technique has different symbol, different level of symbols. Okay, so you see that the value of m is depending on 2 power of k, 2 power of number of bit. Okay, so it can goes from 1 and so 2 here is from this m is from 2 until 256. So the range of m can be from 2 to 256. Okay, so the higher the value of m, that means we are using higher level of modulation. Okay, so what in short you can say that the m is actually representing the level of modulation. Okay, the higher the value of m, that means the higher will be the level of modulation techniques. Okay, so PCM, remember that PCM only use one bit, actually one bit at a time, so that means one symbol only one bit. Okay, for PCM one bit is for one symbol. Okay, if you are using 2 bit, that means we have 2 bit for each of the symbol. Okay. So now let k is equal to log base 2 of m, then bandwidth is equal to capacity divide with the number of bit used uh, uh, for the system. Okay, so the bandwidth is equal to the capacity Okay, divide with number of bit. Okay, so you see that here, since m, okay, m is equal to power of k, so therefore k is equal to log base 2 of m. Okay, and if you see from here, okay, so don't confuse with this equation. So this is actually for the minimum bandwidth. Okay. You might wonder, where is the 2? Okay, where is the 2 actually? So don't be confused about that. This is what we call as a minimum bandwidth. So minimum bandwidth is equal to the bit rate, or here you can say the capacity. Okay, the highest bit rate or the capacity divide with log base 2 of m, where log base 2 of m is actually the number of bits used in the transmission. Okay, and the bandwidth, remember that bandwidth is in terms of hertz. Okay, so k is the number of bits encoded into each signaling element, and you see that c over k. Okay, c over k is also known as the symbol rate. Okay, c over k is also also defined as the symbol rate, which is called as baud. So baud is also equal to c capacity, channel capacity, divide with the channel capacity is the highest bit rate. Okay, the maximum bit rate, divide with the number of bit per symbol. Okay, number of bit for each of the symbol. So you see that k is the number of bit, so therefore you're going to produce symbol per second. Okay, so bit rate here is in terms of bit per second. So bit per second you divide with number of bit that produce the symbol. So therefore you're going to produce a symbol per second. Okay, bit rate is bit per second. And when you divide a bit rate with maximum bit rate with the number of bit, you're going to produce baud or symbol per second. Okay, so symbol per second defines how many symbol that we can transmit in 1 second. Okay, how many symbol that we can transmit in 1 second. Okay, berapa banyak simbol yang kita boleh transmit dalam 1 second. Different from the bit rate. Bit rate means that how many bit that we can transmit in 1 second. That one is a bit rate, bit per second. Whereas for the symbol rate, it is how many symbol that we can transmit per second. What is symbol actually? Okay, symbol, as I put here, this one. If I use 2 bit, that means I have 4 symbol. Okay, if I use 2 bit, I'm gonna have 4 symbol, 4 types of symbol, which is 0, 0, 0, 1, 1, 0, 1, 1. So these are the symbols. Okay, so these are the 4 symbols. Okay, so that means if I use 2 bit, how much is the symbol rate defines how many symbol that I can transmit in 1 second. Okay, let's say I use 2 bit. So the symbol rate define the speed of my system to transmit each of this symbol. Okay, berapa laju saya boleh hantar setiap simbol ini dalam masa, berapa banyak simbol yang saya boleh hantar dalam masa 1 second. Okay, how many symbol that I can send within 1 second. That one is defined as the symbol rate or baud rate. Okay, baud rate, symbol rate. Baud rate atau nama lainnya adalah symbol rate, menyatakan kadar symbol yang boleh dihantar. Okay, the rate of symbol that we can send in 1 second. Okay. Okay, now let's look at the first type of digital modulation, what we call here as the ASK, amplitude shift keying. Okay, so amplitude shift keying means that we do the modulation process of digital data. Okay, we do the modulation with the analog carrier. And this modulation will change the amplitude characteristic of the carrier in accordance with the input. Okay, because input we have two possibilities, logic 1 and logic 0 only. Okay, so now carrier we use these equations, vc cos omega t plus theta. And for the ASK general equations, we have 1 plus VMT multiplied with VC cos omega CT. Okay, so now the difference would be based on the input. Okay, because here input VMT, here we only have possibilities logic 0 or logic 1. Okay, so logic 0 here is defined as a positive voltage, sorry, uh, logic 0 is defined as negative voltage. Okay, logic 0 is defined as negative voltage. Okay, and logic 1 is defined is representing f as positive voltage. Okay, so positive 1 or negative 1. Okay, so in this equation only this parameter will change the output. Okay, so you see that for logic 1, okay, for logic 1, so VMT will produce positive 1. Okay, positive 1, and then multiplied with the carrier, so it will produce the output of 2 VC cos omega CT. And logic 0, for logic 0, okay, the VMT will produce negative voltage. Okay, multiplied with the carrier, so 0 multiplied with anything, it will produce 0 at the output. Okay, so logic 1 and logic 0 will produce 0. Okay, so this is like a switch, on off on off on off, like this. Okay, so you see that here we have the input logic 1, logic 0, logic 1, logic 0, and here is the output. We have a output here. Okay, and then 0, and then 2 VC cos omega CT, like this, and then 0. So if you see here, it looks like on and off. Whenever we have an input 1, it will switch on. Whenever we have input logic 0, it looks like it will switch off. So ASK is also known as the OOK. Okay, the other name is OOK, means on-off keying. Dia juga dipanggil sebagai OOK. You see that it will looks like a switch on and off. So this is the pattern of ASK. Yeah. So for ASK, notice that the baud rate and the bit rate is the same. Okay, because we are using the PCM. Okay. And then here, this is a waveform of ASK. So you see that we have a logic 1. This is the input VMT, logic 1 0 1 0 1 0. So we have the output ASK here, on off on off on off on off. Okay, for different logic, for logic 1 0 1 0 1 0. And then here we have about the spectrum. Okay, what about the bandwidth? Okay, the bandwidth for ASK is equal to 2 times the input frequency. Okay, so for example here VMT we have 3 input. Okay, for example here we have 3 input, FM, 3 FM, 5 FM. Therefore the bandwidth gonna be like this. So bandwidth is 2 times the FM. So if we have up to 5 FM, that means we're gonna have up about 2 times the input frequency. So we have 5 times 2, we have 10 FM. Okay, so this is up to the 5th harmonic. So it depends on how many harmonics in the input. Okay, if we have only one harmonic, only single input FM, so that means the output bandwidth is 2 times FM. If we have the input up to 3 FM, that means the output bandwidth gonna be 6 FM. Okay, it's gonna produce upper sideband and also the lower sideband. Okay, dia akan ada upper and lower sideband. So bandwidth for ASK is equal to 2 times input frequency FM. Okay. So OOK can be done using multiplier circuit. So how can we produce this ASK, or we can say OOK? Okay, so we can use a multiplier circuit. So this is the modulation process. Okay, so you see that here we have a logic 1, input logic 1, logic 0, logic 1, logic 1, logic 0, logic 0, logic 1. And when we want to do the modulation process, we can use a multiplier circuit. So the word multiplier here means that it will do the process of multiplication. Theoretically, it will do the process of multiplication. So you see that here, this is below the picture below here. It shows the carrier, which is a VCT. Okay, this is the VMT. Input is VMT, carrier is VCT, and then we will do the multiplication process. So when we do the multiplication process, you see that input logic 1, so 1 multiplied with this voltage, so it will produce similar to the carrier signal. Okay, and then the next one is logic 0, so 0 multiplied with anything, it will produce 0 output. And then input logic 1, it will produce similar with the carrier voltage. And then another logic 1 again follows the carrier waveform, and then 0 0 off, and then on again. Okay, so this is how we do the modulation process. We do the multiplication with the digital input data. Okay, and for the detection, so we have two types of detection: coherent detection and also non-coherent detection. So for coherent detection means that this is at the receiver. Okay, this is at the receiver. So we receive a ASK signal or OOK wave. So when we want to do a demodulation, we will do the multiplication with uh, carrier information signal. Okay, again in the receiver, when we do the demodulation process, we will multiply again with the same carrier frequency signal. Okay, kita akan membuat proses darab dengan carrier signal, signal yang mempunyai frekuensi yang sama dengan carrier. Okay, we will multiply with the signal that has the same frequency with the carrier. So since we are using carrier information for the demodulation process at the receiver, so this is called as the coherent process, coherent detection. If it is a non-coherent, that means we are not using the carrier information. Okay, so since we are using the carrier information for the demodulation process, so this is a coherent detection. So we multiplied with the input ASK, and then you see that when we multiplied, we're gonna produce. You see that here is the analog. Okay, this is the analog. You multiplied with the analog signal. Actually, you're gonna produce the upper sideband and also the lower sideband, and you need a filter to filter out which part that you want. Either you want the upper sideband or the lower sideband. So this is a low pass filter that in this case it will select the lower sideband and then produce the output. So it depends, if you want to produce analog output, you can just do like this, or if you want to produce a digital output, you need to do some other process to change from the analog to digital. Okay. So demodulation wave can also be done using envelope detector or non-coherent or asynchronous detection. Yes, we can do the non-coherent detection. So the coherent detector is more complicated than the envelope detector, but the results is in a lower probability of error for a given signal to noise input. So it is said here that for coherent detection is will produce a better results compared to the non-coherent. Okay, so now the way how we want to calculate the probability of error, kebarangkalian berlakunya error, P of BE. Okay, PBE this is PBE for the coherent detection. Okay, probability of error for coherent detection is equal to 1 over 2 error function, complementary error function of, this is actually supposed to have bracket. Okay, because all of this parameter belongs to the complementary error function ERFC. Okay, square root of EB over 2 and 0. So ERFC is the short form for complementary error function. So uh, ERFC of Z is equal to 1 minus error function of Z. So this one to show you the relationship of complementary error function and also error function. Okay, where ERF is the short form for error function. So both of these are interrelated to each other. Complementary error function and also error function are related to each other. Okay, so this is the table. So normally the table we give in the final exam, this is the table for error function. Okay, so you see that this is the error function for parameter x. Okay, so x can be from 0.00 until 0.09, for example here. So you see that here the first column is x, the value of x from 0.0 until 3.2. So for example, if I want to find a error function for x equal to 0.40. For example, error function for x equal to 0.40, that means it is this one. Okay, or 0.49, for example. So we're going to produce error function output is equal to 0.55, sorry, 0.51167. Okay, so that's how we find the values for the error function based on the input. Okay, and this is the complementary error function table. Okay, so complementary error function table, here again the values in the tables are different because we are using a slightly different equations. So again, if the x is equal to 0.40, what happened is that the output of complementary error function is equal to 0.57161. If the input x is 0.49, okay, it will produce the output of complementary error function equal to 0.48833. So this is using the table. Okay, given the example, this is for coherent detection of ASK. Calculate the probability of error, kebarangkalian berlakunya error. So you can use P probability of error PBE given EB over N0 0.32. So what you can do is that 1 over 2 ERFC of this one, square root of EB over N0. So you can put inside the equations. Okay, so here you see that it will do like this. Okay, so square root of 1 over 2 EB over N0. So it put aside the 1 over 2. So we can put the 0.32. So you see that 0.32 is put inside the equations. So 0.32 multiplied with 1 over 2. Okay, darabkan dengan 1/2 or 0.5, and then we do the square root. Okay, so you see that ERFC square root of 0.16. So we need to find this one, ERFC 0.4. So this is actually 0.40, 0.40. So we can find from the complementary error function, we can find from the complementary error function 0.40 is actually equal to 0.57161. Okay, so this is 0.5761, 0.57161, okay, 0.57161. Okay, and you see that this is a 0.57161. Actually, you can also do based on the error function table. Okay, so ERFC, you see that the first row here is based on the error function table. So you find the zero point 0.4 from the ERF table. ERF table is from the first table. Okay, from the ERF table, error function table, we get at 0.40, we get here is, you see that here is 0.42839. Okay, 0.42839 is this one from the error function table. We can use the formula to find the complementary error function by using 1 minus error function. 1 minus error function. At the end, we're going to get the same answer. Okay, so that's why in the final exam, normally students needs to choose either you want to use a complementary error function table or you want to use error function table. Okay, so you have the options. So for easy, if you want to make it easy, just use the complementary error function table. Okay, so here you see that so we have found the values. Okay, so we have found the values of ERFC 0.57161. Remember, we need to multiply with 1 over 2. Okay, we still have this parameter 1 over 2. Don't forget about that. Jangan lupa kita perlu darabkan lagi dengan 1/2. So multiplied with 1 over 2. So therefore, the probability of error is 0.2858. Remember, this is a probability value. There's no unit for this one. Okay. And then if we want to use a non-coherent detector, okay, jika kita menggunakan non-coherent detector pada receiver, so therefore the probability of error. So before that, maybe I need to add more explanation. So this probability of error is actually defined as the probability of bit error after the decoding process by the receiver. Okay, so how much is the probability that the receiver will produce error at the output? Berapakah kebarangkalian berlakunya error pada receiver selepas receiver melakukan proses decoding? Adakah receiver do the receiver can uh, produce the exact output same as the input? Uh, so this is actually the measurement done in the receiver side actually. Okay, we want to know the receiver capability. Okay, we want to know the receiver capability to decode the received signal. Okay, how much would be the probability of error produced by the receiver? Okay, so that's why it is based on the detection type, coherent or non-coherent. Okay, so this is actually happens at the receiver side. Okay, so and if we use the non-coherent detection, okay, it the equation will be slightly different where we don't need to use the table. Okay, kalau kita menggunakan non-coherent, we don't need to use the table. Instead, we can use the formula. So this is the formula for probability of bit error. If we use ASK for the ASK non-coherent detection. Okay, so probability of bit error is equal to 1 over 2 exponent power of, okay, e power of minus EB over 2 and 0. Okay. So this is in, I put bracket here because this is belong to the function of e or exponent. Okay, so E here you can find from your calculator. Okay, from my calculator, I can use E by pressing the button of Shift Lon. If you press my calculator is a Casio FX570MS. So here you can find if I'm using my calculator, I should press Shift Lon and I can find and it will produce a E power of something like this. Okay, so I just need to put the value. Okay, the value. Okay. So here, given EB over N0, 1.11, find the probability of bit error if you use a non-coherent detection at the receiver. So this define how much is the error probability at the receiver side, how much is the error probability that the receiver will produce after decoding process. So it uh, defines the capability of the receiver to decode the signal, whether how much is the difference from the output and the input. We want to compare the output and also the input signal transmitted from the receiver. Adakah dia sama atau berapa banyak berlakunya error. Okay. So probability of bit error here is equal to 1 over 2 e power of negative eb over 2 and 0. So you can put aside negative 1 over 2 multiplied with eb over n0. Eb over n0 is given as 1.11. Okay, 1.11 multiplied with negative 1 over 2, so it is e power of negative 0.555. So this you can use calculator to find this one. You can straight away using your calculator, using your calculator. So e power of negative 0.555, it will produce 0.5741. Okay, this is using the calculator and then multiplied with 1 over 2. So you will produce the probability of bit error equal to 0.2870. Okay, so for the non-coherent, we don't need to use the table, error function table or complementary error function table. Just straight away using the calculator. And then we have the second type of digital modulation technique, which is the frequency shift keying, FSK. So the general equation for the FSK is equal to VC cos in bracket 2 pi fc plus vmt delta ft like this. So the thing that gonna change here is vmt. Okay, vmt is depending on the input of logic 1 and also logic 0. Okay, so logic 1 will produce a positive output voltage. Logic 0 will give a negative voltage. Okay, so logic 1 representing by positive voltage, logic 0 representing by negative voltage. So we are using actually bipolar. So back to the equation, you see that here is if let's say we have a logic 1, so VMT is representing by positive 1 volt. Okay, so therefore here is this is actually positive 1. Okay, positive 1. So you are supposed to this is supposed to be cancelled out. So you don't need to put VMT here. So it is actually VC cos 2 pi, okay, in bracket fc plus delta f actually. Okay, so vmt here is actually has been substituted with positive 1. And if the input is logic 0, so vmt is represented by negative 1. So here you don't need to put vmt like this, just put minus 1 here. This is actually minus 1. Minus 1. So this is actually vc cos 2 pi fc minus delta F. Okay, because we already substitute the VMT with positive 1 or negative 1. Okay, kita telah gantikan nilai VMT dengan positif 1 ataupun negatif 1. So you see that the bit rate and baud rate of FSK is equal since we are using only one bit. So that's why the bit rate and the baud rate is equal. But the bandwidth can be approximated by using a Carson's rule, which is, you see that here, 2 times delta F plus B. B here is actually the frequency of FM, actually, the frequency of FM. Okay, so this is the bandwidth of FSK. So how we want to produce the FSK signal? We can see here, this is the process of modulation techniques. Okay, so you see that the first picture A and B. So picture A here, you see that we use a multiplier. And we use two types, two values, two different oscillator with different frequency. Okay, so we have the input here is 101, and then this 101 is put inside this first modulator. Okay, the first modulator here, I can see that this is a second modulator. Okay, and then here you see that it has an inverter. Inverter will change the state. So logic 1 will change to logic 0, logic 0 will change to logic 1. Okay, so that's why after the inverter it becomes 0 1 0. So we invert, okay, we inverse the input. Okay, terbalikkan input tersebut. So it becomes a 1 0, a 0 1 0, and put inside the second modulator, and we do the so inside the modulator we do the multiplication process. So you see that here in this example, the first oscillator has higher frequency compared to the second oscillator F2. So in this example, actually F1 is larger than F2. Okay, so when you multiplied uh, f1 with the input, okay, when we multiplied f1 with the input, what happened here is like this. We're going to produce on and off. So this is like the on and off keying, actually. So you see that we multiplied with logic 1, so we have the output followed by using the so the output here follows the first oscillator frequency, and then input 0 multiplied with F1, so off, nothing. 0 multiplied with anything going to produce 0. And then input logic 1, so it will produce output like this, which has the similar frequency with the first oscillator. And then if we see from the second modulator, what happened is that F2 multiplied with the input. Remember that F2 has lower frequency than F1. Okay, so what happened at the output is that when you multiply again 0 multiplied with anything, it will produce 0, nothing. And then F2 multiplied with the input 1, so it will produce the output on. Okay, it will on, so that means it has the output which follows the oscillator frequency. In this case, you see that the graph showed like this. That means it want to show to you that the F2 frequency is much smaller than F1, because if you have a high frequency, it will become like the first modulation process, the above part. So F2 is lower frequency, so you see that the wave like this. Okay, and then for the next input 0, it will produce 0 output off. So you see that here for the second modulator, it will switch on at the second bit time. Okay, first bit time is off, second bit time it will switch on, third bit time it will off. Okay, and then we put inside the summer addition process. So you see that above and below we're going to do the addition process. So you see that for the first bit time, so it will follow for the first output of modulator. Second for the second bit time, you see that this one is the above modulator produce 0, the above modulator is off, whereas for the here we have uh, for the second bit, the second output modulator is switched on. So 0 plus something, so 0 plus this waveform A0, so we're going to produce a output like this. Okay. So pada masa bit yang kedua, yang modulator pertama adalah switch off, modulator yang kedua mempunyai output signal. So when we sum together, we're going to produce this waveform. And then you see that for the third bit time, pada masa bit yang ketiga, the second modulator produce 0 output, whereas for the first modulator produce output like that. Uh, has the output switch on. So you see that this will go to the uh, third for the third bit time. Okay, the third bit time here is a signal you plus with 0, so you're going to produce this one. So because this is 0, so 0 plus uh, something with a voltage, so you're going to produce according to the first modulator. Okay, dia akan ikut seperti output modulator yang pertama tadi. Okay, so you're going to see that what happened to the output actually. Okay, what happened to the output is that you're going to see a high frequency. Okay, high frequency, and then low frequency, low F, high frequency. I see that the third one is high frequency. Okay, so high frequency, low frequency, high frequency, low frequency, and so on. So in FSK, you're going to see the output difference in terms of frequency. Okay, only two possibilities of frequency happens here. Okay, for the input logic 1, it will produce a high frequency. For the input logic 0, normally it will produce the low frequency of signal, output signal. Okay, so different from the OOK or ASK, where we have a output signal and then turn off, and then output signal and then turn off. For the FSK, it will produce the output difference in terms of frequencies. So already azan prayer time. And if you see from the picture below here, you have the binary input. So this is actually the same as this one, the same as above part actually. So there are many processes happens here where it will produce a high frequency and low frequency for the output. Okay, so in this frequency modulator, um, there are actually a few sets of circuits inside here which produce a high frequency and low frequency, and you can see that here is 101. So input logic 1 will produce a high frequency, input logic 0 will produce low frequency, low F. Input logic 1 will produce output high frequency. Okay, so so that's for the signal generation, FSK signal generation. So I stop, I pause for a while for to respect the Azan prayer. So I pause my lecture for a while until the Azan prayer finish. So based on these slides, you can say that the way we generate the FSK is that the circuitry needs to produce two sets of frequencies in the output. High frequency for the input logic 1, low frequency for the input logic 0, so we have two sets of frequencies, high frequency and the lower frequency. So this is much different from the FM in the analog, where we have where the frequency change according to the input variations. So now, since our input is only have two states, logic 0 and logic 1, therefore we only have two possibilities of output frequency, high frequency and low frequency, only two possibilities like that. Okay, and this is the shows the input and also the FSK output. Okay, so above here is the input PCM code word, PCM binary input, and we have here the below one here is for the FSK waveform. Remember, for the input logic 0 will produce output of low frequency, and input logic 1 will produce high frequency at the output. So for the low frequency, we call it as FS, space frequency. For the high frequency, we call it as FM, mark frequency. So this is just the terms used for the to represent the output frequency of the FSK, space mark, and so on. Okay, so and TB is a 1 bit time. Okay, and what happened to the, okay, this is a table to show the relation of input and also for the output. Okay, so you see that here for the input of 101010, okay, input 101010, and the FSK waveform looks like this, high frequency, low frequency. Okay, you see that here is high frequency, low frequency, and then high frequency input logic 1, low frequency input 0, high frequency logic 1, and low frequency for the input logic 0. And if you see from the perspective of bandwidth, the bandwidth for the FSK, we can use the Carson's method, which is 2 times Fm plus delta F. So it is depending on how many harmonics in the input. If the harmonics is up to 5 harmonics, like in this example, that means our formula for the bandwidth is 2 times 5 Fm plus delta F, because we're going to have upper and lower sidebands. Okay, so this is follow the Carson. And this is for the detection process in the receiver. Okay, how we want to produce the output data. Okay, so you see that here we have a FSK input, and then we have the power splitter to split the different set of power. Okay, so and then it goes to the first multiplier and second multiplier. So in the multiplier, we multiplied with the carrier. So carrier, here we have two different carrier frequencies. Okay, so when we multiplied with the carrier, remember that we're going to produce LSB and also the USB. Okay, remember in the chapter 3, multiplication process will produce lower two parts, LSB and also the USB. And we're going to use a low pass filter to select the lower sideband. Okay, and for here, this one will produce a positive output, and this is the negative logic. Sorry, positive here is a logic 1, log logic 1, sorry. So here the output here is, if you see that here is plus, okay, plus, so and this is the minus. So whatever the output here, it will do the with addition with the minus, so you're gonna produce a minus. If it is a minus, means that logic 0. If it is plus, you're gonna produce logic 1. Okay. And then here, picture below is for the non-coherent. Non-coherent means that we are not using a carrier information. We are not multiplying with the carrier signal frequency. So here we use a band pass filter to separate the space frequency and also for the mark frequency. Okay, so we use a band pass filter to select the space frequency, or band pass filter here to select the mark frequency. So we are choosing the high frequency and low frequency, and then put inside the envelope detector. So envelope detector will change uh, envelope detector will change the different of frequencies here, change into a different set of output. Okay, so the output that you will produce is 101010. Okay, so positive voltage will representing by logic 1, negative voltage will produce 0 at the output. Okay, and here is the probability of bit error for the coherent FSK. So probability of bit error for the coherent FSK follows the same equation as the ASK, sama seperti ASK. Okay, same 1 over 2 ERFC EB over 2 and not. And then this is okay, this is similar. Okay, for the non-coherent, the probability of bit error for the FSK also the same like ASK, sama seperti ASK, like the previous ASK. Okay, so it used the same probability of error, same equation with the ASK. Okay, now let's look at the third type of modulation, digital modulation technique, which is PSK. Remember, PSK is quite similar with PM in the analog. Okay, where the modulation process will change the phase of the carrier in accordance with the input. So proses modulation ini akan mengubah fasa carrier berkadaran dengan perubahan input. But now the input, we only have two possibilities of input, either logic 0 or logic 1. So you see that since the beginning we only use one bit actually. So in your lecture notes, we are actually seeing the use of one bit only. Okay, either logic 0 or logic 1, because this is about PCM waveform. So this is related to the PCM, where we only process, this is related to only one bit binary. So since we're using one bit where we have two possibilities, okay, 2 power of n, 2 power of 1. So we're going to have two possibilities of input logic, which is logic 0 or logic 1. Okay, so here if we are using only one bit, that means this is called as the BPSK. So BPSK, if you want to write in terms of M array, it is actually equal to 2 PSK. Okay, 2 PSK is also known as the binary phase shift key. Remember, we can also write in terms of M PSK. So this M is actually equal to 2. Okay, this M is equal to 2 for the BPSK. Okay, so okay, so in BPSK, the difference of phase between input logic 1 and logic 0, okay, between input logic 1 and 0, the difference of phase is about 180 degree. Perubahan fasa itu adalah sebanyak 180 darjah. So there's a lot of difference in terms of phase. So the changes from 1 to 0 or 0 to 1, the difference would be 180 degree. Okay. And this is a block diagram for BPSK, binary phase shift keying signal. How we want to generate the BPSK. So you see that here for the input, you see that we have input unipolar, and then we have a level converter to change from unipolar to bipolar. So we have the output here with two different polarities, positive and negative voltage. So positive voltage for the input logic 1, and negative voltage for input logic 0, logic 1, and so on. And put inside the balance modulator, we're gonna do the multiplication process with analog carrier. Here, the analog carrier, we use a sine wave, sine omega ct. Okay, so here you see that when we multiplied with this input, we're gonna produce okay, you're gonna see later what is the equations, okay, and so you're gonna see what happened here. Okay, so you see that actually the output here is you see positive multiplied with sine, you're gonna produce a positive sine. And if you multiply negative voltage with sine, you're going to produce negative sine. Negative sine is inverse like this. Okay, so you have a positive sine and a negative sine wave, and then we can use band pass filter to select which waveform that we want, and then we transmit. Okay, so here you see that from here this is for the receiver side. Okay, so we have the BPSK input. So here actually what we send from the transmitter, we send sine wave or we send the negative sine wave depending on the input. So if it is the input logic 1, we're gonna transmit sine wave, sine omega ct. If it is for the input logic 0, we're going to transmit negative sine wave. Okay, and you see that for at the receiver side, so the BPSK input for positive sign, or we have the negative sign. Okay, we have two possibilities because this is a BPSK, so we have two possibilities. And here we have a band pass filter, so we need to filter out the signal. And then here we do a demodulation process. So this is a coherent detection where we multiplied with the same carrier signal. When we multiply two analog signal, we're going to produce LSB and also the upper sideband. And then we put inside the low pass filter. So since we use here low pass filter, that means it will select the lower sideband. And then level converter, this is to change back from bipolar to unipolar. We are doing the reverse process. Okay, so we get the unipolar at the output. Okay, and this is the equations. Okay, so this is the equations for the okay, this is the equations for the in the receiver side. Okay, in the receiver side. So you see that at the receiver side, we will receive positive sign, or we also will receive negative sign at the receiver. Negative sign omega ct or positive sign omega ct. Okay. If you see from here, okay, this is for the this is for the transmitter side. Okay, so you see that if we multiplied sine with positive voltage, it will produce positive sine wave. If we multiply negative voltage with sine wave, it will produce negative sign. So actually what we transmit over here, either sign, positive sign or negative sign, either two that we transmit. So in the receiver, so you see that means we will receive either positive sign or negative sign at the receiver. Okay. So you see that for the input signal at the receiver, if it is a positive sign, that means we are actually receiving logic 1. Okay. So how does the process happens? You see that at the balance modulator, okay, at the balance modulator, so if the input is positive sign, okay, we multiplied with this carrier signal again, sine wave. So positive sign and another positive sign. Okay. For example, this is the input. Okay, the input is logic. The input is positive sign, and this is the carrier. When we multiply two of these, we're going to produce sine square. So sine square, according to trigo identity, we will produce this one, 1 over 2, 1 minus cos 2 omega ct. Okay, so this is according to trigonometry identity. So in this case, what we produce actually 1 over 2 minus 1 over 2 cos 2 omega ct. Okay, so from here you see that here is a constant value, and here is a high frequency signal. Okay, so this is a DC value, actually DC value 1 over 2 volt, and also we have an analog, sorry, we have the AC value here, which is cos 2 omega ct. Since we have a filter over here, low pass filter, LPF, so low pass filter will filter out the high frequency signal of this one. This is a high frequency, so it will be filtered out by the filter. So after the filter, we're gonna produce a DC voltage of positive 1 over 2 volt. So positive voltage is actually representing by logic 1. Okay, logic 1. And then let's look what happened if we have input minus sine omega ct. So now different thing. So now let's say we have input at the receiver minus sine omega ct. And remember from what we have learned from the transmitter, if it is a sign, negative sign, actually we transmit logic 0 actually. So we are expecting, okay, we are expecting to see the output is supposed to be logic 0. If the output is not logic 0, that means there's going to be error. Okay, we are expecting logic 0. So now we are receiving negative sign omega ct. So how does the receiver will decode this information? Okay, so you see that the output of the balance modulator, okay, output of the balance modulator, so we receive the input here, negative sign, and then we multiplied with sine. Here we multiplied with sine omega ct. Okay, so sine omega ct multiplied with negative sign, so we're going to produce negative sine omega ct. So negative sine omega ct, and then we change, we do the trigonometry identity, minus 1 over 2, 1 minus cos 2 omega ct. Okay, so we have the DC voltage negative 1 over 2 plus AC voltage here 1 over 2 cos 2 omega ct. So these high frequencies, you see that this is a high frequency, 2 times the FC, 2 times the FC. So we can use a low pass filter to filter out this one. So after low pass filter, we can cancel out this component, and we can produce the output only DC voltage negative 1 over 2 volt. So you see that the output of the filter, the output of the low pass filter is negative 1 over 2. So negative voltage when we do when negative voltage is represented by logic 0. Now, remember, negative voltage represented logic 0, positive voltage represented by logic 1. So in this case, the receiver uh, decode correctly produce logic 0. Okay, so you see that this has been asked previously in the long time ago in the test and final exam, where the students needs to find the equations. Okay, to find the equations. This simple equation like this. So what happen if the input is sine omega ct? What happen if the input is negative sine omega ct? So shows the equation what is the output logic values. So this has been asked in the previous tests and exams previously, long time ago. Pernah ditanya, pelajar diminta untuk derive the equations after the what happened based on the input. You are given the input and you need to find the output. Very straightforward. This is it because we only have two possibilities: positive sign or negative sign. That means the output is only two possibilities, either logic 1 or logic 0. Okay, and besides that, this is for the what we call as the truth table. A is a truth table, B is a phasor diagram, C is the constellation diagram. Okay, so what is this actually? So this is not only for the PSK, actually for the FSK and ASK also, it has the truth table, phasor diagram, and constellation diagram. Okay, untuk FSK dan juga ASK juga sebenarnya ada dia punya diagram. But in this lecture notes, we just want to give an introduction to you based on the BPSK. Okay, so based on the BPSK, you see that for logic 0, logic 0, okay, so you see that logic 0, remember that for logic 0, actually we are transmitting negative sign. Okay, for logic 1, we are actually transmitting positive sign. Okay, remember this is a negative sign. This is a positive sign. Okay, so you see that for logic 1, for positive sign, there's no changes for the phase. So the sine wave follows the phase of the sine wave. There's no difference from it starts from 0. It starts from 0. There's no the output of phase is actually the difference is 0 degree, because we start from 0 degree until 360. Okay, and different from the negative sign for the logic 0. Okay, logic 0, the sine wave is inverse. Okay, sine wave ini diterbalikkan menjadi, it becomes a negative sign. So what happened is that it starts from here, which is starts at negative 180 degree phase shift. Okay, it shifts at 180 degree below like this. Dia berlaku perubahan fasa 180 darjah. Okay, we start towards like this 180 degrees. So that's why we're gonna see this is the output phase is actually 180 degree, whereas for logic 1 actually we start at phase 0 degree. Okay, and this is a logic table for BPSK. We only have two possibilities: logic 0, logic 1. So logic 0 for the negative sign, which is actually the output phase is negative 180 degree. And for the logic 1, sine wave, positive sign, so the output phase is 0 degree, because we start with 0 degree. Nothing changed with the output phase. There's no changes in the phase for the positive sign, whereas for the negative sign is actually inverse from the positive sign, so it is actually 180 degree shift. Okay, So, and when we draw the phasor diagram, phasor diagram is also known as the arrow diagram. So you see that this is to see the difference of output in term of phase. We want to see the difference in term of phase. Kita nak lihat perubahan output dari segi fasa tersebut. So you see that for here for logic 0, okay, for logic uh, for logic 1, actually the phase is 0 degree. So remember, this is if you draw, this is 0, 90, this is 180, this is 270, and then back to here 360. Okay, so 0 degree phase is for the logic 1, so that means the arrow is showing to the right directions. And for logic 0, it is a 180-degree phase, so it is shows the arrow towards 180 degree. So we have this is for the logic 1 and logic 0, because we only have two possibilities. That's why if we have if we go to the higher level modulation technique, actually we're gonna have many errors, many arrows like this. Okay. This is if we go to higher level of modulation techniques. But since we are using only BPSK, BPSK only has two possibilities because we only use 2 bits, sorry, 1 bit only. So we have two possibilities of output. So that's why you only see one arrow like this. If we go to higher value of M, okay, if we have many symbols, okay, if we go to higher value of M, we're gonna see the many arrows here in the phasor diagram. And another one is constellation diagram, to see uh, the arrangement of the constellation. Okay, so again, this is based we want to see the difference in terms of phase. So you see that here again, this is from 0 degree, 90 degree, 180 degree, 270 degree, and then 360 degree. Okay, so since the logic 0 is located at 0 degree, so it is here. And sorry, logic 1 is located at 0 degree. Logic 0 is located at 180 degree, which is here. So we have two dot here. Okay, ada dua dot di sini. And again, if we use a higher level modulation, we're gonna see a few sets of constellation. Maybe somewhere here, somewhere here, somewhere here, somewhere here. Actually, if we go to higher level modulation, okay, if the value of M is higher, that means we're gonna have many symbols. So now you're gonna see that each of these constellation is representing as symbol. So I erase this one. We are using BPSK. BPSK only consists of two symbols. Okay, logic 1, symbol for logic which is 0 and 1. Two symbol only. M equal to 2. Okay, so that's why we're gonna have two constellation only. Okay, two dots only. Okay, so if let's say I use 2 bit. Okay, if I use 2 bit, that means if if number of bit is equal to 2, that means I gonna have 4 symbol, which is 0 0 0 1 1 0 1 1. Okay, so this is for M equal to 4. Okay, for M equal to 4, which is this is what we call as a QPSK. Okay, QPSK is different. That means we're gonna have 4 dots here. Okay, somewhere like this. So it is not in the syllabus. I just want to show you that. So we have 4 dots. So each dot is actually representing a unique symbol. Setiap dot ini mewakili satu simbol. Okay, similar with this phasor diagram, actually we're going to have 4 arrows like this if it is for the QPSK. Okay, so now since we are using BPSK only, so we only see 2 arrows on the right and to the right and to the left. Okay, so what is this for actually? What is the purpose of this constellation and phasor diagram? So constellation diagram and also the phasor diagram, we want to see uh, the how close one symbol to another in terms of phase. How much is the distance from one symbol to another symbol in terms of phase? Kita ingin melihat berapa dekat jaraknya antara satu simbol dengan simbol yang lain. Okay, if we go to higher value of m, okay, if we go to higher value of m, we're gonna have many dots over here. Okay, many dots over here, and we're gonna in the analysis actually, when there are many dots, that means each symbol is close to one another. Okay, one symbol is close to one another symbol. That means the chances of error happens will be higher. Okay, if the symbol is separated far away, that means the error gonna be less. Okay, kalau simbol itu terpisah jauh, if the constellation is separated far away, that means both of these symbol is will produce a less error. The chances of having error is smaller compared if we have many constellation which is close to one to another. Okay, kalau kita ada constellation yang rapat-rapat, dot itu terletak pada jarak yang dekat-dekat, maka kebarangkalian untuk berlakunya error will be higher. Okay, compared to if the distance is far away. So that's why in the constellation diagram, we want to see the distance actually in terms of phase. Okay, so that's why if we go, that's why the modulation techniques that we do, it actually in practical cases, we want to go to higher modulation techniques. Okay, but we also needs to be careful with um, the symbols, because when we go higher modulation techniques, we have many symbols. That means the location of the constellation will be close to another, and it is more prone towards the error. Okay, and this is the waveform of BPSK. Okay, binary phase shift keying. So you see that here we have input logic 1 0 1 0 1 0. So remember input logic 1, as we have learned previously, input logic 1 will produce positive sign, input logic 0 will produce negative sign. Okay, so from here you see that input logic 1 produce positive sign. Okay, and input logic 0 will produce negative sign. Input logic 1, positive sign. Okay, positive sign. Input logic 0, negative sign. Positive sign, negative sign. Okay, so what happened if it is a 1 1 like this? What happened? Okay, so what happened is that I will show you, because previously we asked the student with different sets of input. So if it is a input logic 1 and input logic 1, for example, here is 1. So you can draw like this. It is a positive sign and then positive sign again. Okay. And then, sorry. And then positive sign again. Okay. If it is 0, that means it will negative sign. So you see that from here, you see that here, this point, this is different in terms of phase, 180-degree phase shift. So this shape like this, this shape. Instead of going down, is going up like this. Okay, instead of going down, it goes up. So the difference in terms of phase is about 100 degree. Okay, perubahan fasa sebanyak 180 derajat terbalik, inverse. Okay, so positive sign, negative sign, and so on. So this is a BPSK waveform. Remember, waveform is in term of time domain, so this is actually voltage versus time. Okay. And here you see that this table wants to show the relationship of VMT and the output. Given the input here is, given the input here is 101010, what is the output here? So the output here is, you see that here, input logic 1 will produce positive sign, okay, and then we have input logic 0. Input logic 0 will produce negative sign, okay. Input logic 1 will produce positive sign, okay, will produce positive sign. Input logic 0 will produce negative sign, and so on dan seterusnya. Okay. So about the bandwidth for the BPSK, okay, the bandwidth for the BPSK. So you see that here the bandwidth of the PSK is follows. The bandwidth of PSK is equal to 2 FM. Okay, the bandwidth of PSK is equal to 2 FM. So the bandwidth of PSK is similar with the bandwidth of ASK. Okay, so if we have up to 5 harmonics at the input, that means the output that we produce is equal to 2 times 5 FM. So we have 10 FM. So the bandwidth is going to be 10 FM if we have up to 5th harmonic. So it depends on how many harmonics at the input. Okay. And then regarding the probability of bit error at the receiver side, so the probability of bit error for the PSK is different compared to ASK and FSK. Dia berbeza dengan FSK dan juga ASK, where you see that the difference is there's no 1 over 2. Here you see that here over this one there's no 1 over 2. Okay, compared to the ASK and FSK, the probability of bit error we have 1 over 2 ERFC in bracket square root of EB over 2 and 0. Now in PSK, there's no 1 over 2. The difference is only, the difference with the previous one is there's no 1 over 2. Okay, tidak ada 0.5 di sini at this point. So this is the difference is it's not 1 over 2, so it is square root of EB over N0. This is for the coherent PSK. And for the non-coherent PSK, you see that there's also slightly different for the non-coherent, where there's no 1 over 2. Remember that in ASK and FSK we have 1 over 2 e power of EB, negative EB over 2 and 0. Here for the PSK, the equation don't have the 1 over 2, so therefore it is a 1 over 2 e power of negative EB over N0. Okay. So in terms of probability of bit error, PSK is different from FSK and ASK. Okay. And okay, already finished. Already complete chapter 4. Okay, chapter 4 already complete. So for the final exam actually is up to the PCM actually. So actually if you listen to my first part video, it is enough for the final exam. Okay, so here I straight away for the part 2 until digital modulation, so you hopefully you can understand about baseband transmission and also the band pass transmission. Okay, So we have the line coding for the baseband transmission. We have the ASK, FSK, and PSK for the band pass transmission for the digital techniques. Okay, so uh, yeah, uh, that's all for chapter 4. So we next week we will start with chapter 5. Chapter 5 is about uh, antenna and wave propagation. So actually chapter 5 is about transmission line, antenna, and wave propagation. So there are actually three main topics in chapter 5. Okay, we will learn later transmission line, antenna, and also the wave propagation. Okay, so that's all for now. So see you again next week. Okay, so next week we're gonna do the normal class. We're gonna have a normal class through Google Meet. Okay, so that's all. Bye bye.